Hi everyone, this is Shuvomoy Gupta. I am also known as Shuvo. I am a second year PhD student at MIT Operations Research Center. This is a joint work with Professor Bartholomew Stellato at Princeton and Professor Bart Van Parijs, who is my supervisor at MIT Sloan School of Management. The title of my talk is NExOS.jl, a Julia package for non-convex exterior point operator splitting. So NExOS is an acronym of the algorithm that we are proposing, non-convex exterior point operator splitting. So this is an algorithm to solve non-convex optimization problem. So before we look into the algorithm itself and the Julia package, let's take a look at the optimization problem in consideration first. The problem is consideration has this following format, and this is very common in machine learning and statistics. We are trying to minimize a convex loss function plus some regularizer term subject to the decision variable lying in some constraint set x. So in our setup, x can be a matrix or a vector or a combination of both. So for a vector, the norm is Euclidean norm, and for a matrix, the norm is the Frobenius norm. So this constraint set x has the following structure. X is an intersection of a compact convex set C and a structured non-convex set N. So compact convex set, actually it can be any compact convex set, but for the purpose of our talk, like we could imagine that C is a ball with large enough radius around the center 0. As for the non-convex set N, why we are calling it structured? Because it has a special property. Projection onto this set N is single valued around local minima. And this type of sets are called prox regular sets. So let's take a look at an example. On the left-hand side, the set that we are looking at, this is a non-convex set. Why this is non-convex? Because if we take these 2 points and create this chord, part of this chord lies outside the set. So this is non-convex by definition. Now, if we consider this point P, at this point P, the set is actually not prox regular. Because on the right-hand side, if we take a look at this point P, and we have constructed this ball, right? Now, in this ball, we can see that, okay, there is a point X where from this point, there are 2 equidistant projections onto this set. So, and no matter how large or how small I make the radius of this particular ball, there will always be one set point. So at P, the set is not prox regular. However, if we consider this point that I'm showing using my mouse, at this point, we can find a ball around which the projection will be single valued. So in this, on this point, the set is prox regular. So this seems to be a very technical condition. So are there any real life examples of such sets? So it turns out that there are many sets which satisfy this prox regularity property around local minima. Notable examples include sets containing sparse and low rank constraints, weakly convex set, proximally smooth sets, and so on. Furthermore, any closed set is prox regular almost everywhere. And as an example, I am showing this very highly non-convex set on the right-hand side. So believe it or not, this set is prox regular everywhere. So this picture is taken from the book called Variational Analysis by Rockefeller and Wetz. So in summary, this is the problem that we are considering, minimizing convex function plus regularizer term subject to x in some constraint set x. Now, because n is prox regular and C is compact and convex, we can show that the constraint set x too will be prox regular around local minima. And we call this problem P. So why should we care about this problem structure? Because it turns out that it arises in many machine learning problems. For example, sparse and low rank sparse and low rank optimization problems. I have given a few examples. Not only that, problem with a closed non-convex constraint set is also a good fit for our algorithm. So in terms of related work, the literature in this field is huge, so I will not cover everything, but there are 2 broad approaches to tackle this type of problems. One is the convex relaxation approach, where people convexify the problem. For example, lasso and nuclear norm based heuristics for sparse and low rank models, respectively. Under certain assumptions on the data, this algorithms, this convex relaxation approach approaches can recover the exact solution. However, in many situations, non-convexity of the original problem must be confronted. So to address the non-convex problem directly, there are two approaches that we can see in the literature. One is solving the problem exactly via formulating it as an integer programming problem, and then using some commercial solvers such as Gurobi and Simplex. And the other approach is applying first-order algorithm directly to the non-convex optimization problem. So where does our work fit in? So our algorithm NExOS is a first-order algorithm. In other words, it's only using gradient or subgradient information of the underlying algorithm. So it's non-convex, of course, is tailored for non-convex machine learning problem. An exterior point, it means that in our case, the iterates move from outside of the constraint set toward inside of the set. So an interesting fact is that the term exterior point was coined by Fiocco and McCormick in the 1960s. When they also worked on the interior point algorithms as well. However, like their algorithms were tailored towards convex optimization problem, whereas in our case, we have used operator splitting machinery in designing our algorithm and convergence for non-convex problems. So what are our contributions? We provide a geometric insight into the problem structure. Then exploiting that problem structure, we propose our algorithm NExOS. And finally, we have also implemented our algorithm in the open source Julia package NExOS.jl. The outline of the rest of the talk is as follows. First, I will talk about the exterior point formulation of the problem P. I will talk about my algorithm and the convergence analysis. So this is, I will discuss very briefly, and then I will discuss how to solve problems using the Julia package in NExOS.jl, and I will show a couple of examples. For more examples, of course, you can take a look at the paper or the GitHub repository of the package. So the development of our algorithm has two phases. One is the exterior point formulation of P, and then the main algorithm. So before we go into the exterior point formulation, recall that any set X has this notion of indicator function. This indicator function of any set is defined as follows. If the point X lies in the set is consideration here is our constraint set X, then the indicator function of this set evaluates to 0. And if the point lies outside of the set, then it evaluates to positive infinity. So using this indicator function notation, we can write our original optimization problem as an unconstrained optimization problem, right? Which here the indicator function is forcing the point X to lie in the constraint set. So of course, this is a cosmetic change. Nothing has actually changed fundamentally. We are only rewriting the problem using a different notation. However, the next step is we replace this indicator function Ix with its Moreau envelope, which is an under approximator of the indicator function globally, and is defined as follows. Mu Ix is equal to 1 over 2 mu, where mu is a positive penalty parameter, times distance squared from the set X. So using this Moreau envelope, we can write the exterior point formulation of our original problem, which is a penalization of the original problem. And it turns out that as mu goes to 0, the Moreau envelope actually goes to the original indicator function pointwise. So, so note that we have what we have done here, like in this exterior point minimization function. It has two parts. In the first part, we have the convex function f, which is our loss function. Then in the second part, we have connected the Moreau envelope with the regularizer term. And we call this whole thing mu Greek Ix. So we have split our objective into two parts. In the first part, we have the convex loss function f, which is convex everywhere. And in the second part, we have the Moreau envelope plus the regularizer term. And we can show that this second split function, though is highly non-convex in its original form P, this approximation is locally convex and differentiable around the local minima. So to understand what's going on, let's take a look at a picture. And one-dimensional example of how good of an approximation is this particular exterior point minimization formulation. So we have a convex function f over some Prox regular set. And this particular function, one-dimensional function, you can see that it has two local minima, one at -1 and one at 2. Now, when our penalty parameter is larger, for example, mu equal to 1, the exterior point minimization function is not a good approximation of the original function, as you can see. However, around the local minima of the original problem, we can see that there is a large radius around which the exterior point minimization function is strongly convex and smooth. Like, this is something we proved, but as you can see, it appears to be smooth and strongly convex. And if we look at the local minima of the exterior point minimization function, we can see that it's quite far from the original local minima. However, around this local minima of the original problem, there is a radius of convexity, and this particular local minima falls within that radius of convexity. Now, of course, at this point, this is not a good approximation of the original problem. So let's reduce mu a bit more. So as you can see, as we are reducing mu a bit more, now x mu2, which is the local minima of the exterior point minimization function for the new value of mu, it has come closer to the original local minima x bar. However, another thing to note is that around this x bar, the region of convexity has shrunk a little bit. But good thing is that x mu2 is coming closer to the x bar point. We have reduced mu a bit more. X mu3 is even closer, but the region of convexity seems to be smaller. Mu 10 to the power -4 for all practical purposes. X mu4 is very, very close to x bar. And the radius of convexity is much smaller now. So if we combine all these pictures together, we see that early on, for larger values of mu, we have a larger radius of convexity, but the local minima of the exterior point function is further away from the original local minima. And as we reduce mu, we see that the region of convexity is shrinking, but the local minima of the exterior point function is coming closer to the original local minima. So based on that, we have the following intuition. So these are the same things, what I just said. The intuition is that if we have a local optimal solution to p mu, which is the exterior point minimization function, for example, let's consider x mu1. So for some value of mu1, we have this particular local minima of the exterior point function. Now, if we reduce our mu in a controlled way, so then we can find x mu2 by starting our algorithm at x mu1. So what we will do, we will continue this chain of operations. So where we will start with some larger value of mu, where the region of convexity is larger, find the local minima of the exterior point minimization function, set it as an warm starting point for a smaller value of mu, and we can show that our algorithm will converge to the new local minima, which will come closer to the original local minima. And this process will continue until mu is small enough that we can take the local minima of the corresponding exterior point function to be a good enough solution. And this leads to our algorithm. So now let's take a look at our main algorithm. So it works as follows, roughly speaking. So we will apply a sequence of outer iterations to solve the exterior point minimization problem with decreasing mu. We have, for each value of mu, we have an outer iteration algorithm, which will be a variant of the so-called Douglas-Radford splitting algorithm. And this is where our term operator splitting is coming from, because Douglas-Radford splitting is an operator splitting algorithm. Solution to previous outer iteration will act as a warm starting point or initial point for the new outer iteration algorithm. So we will start with some larger value of mu and strictly decrease mu until some very small value of mu min is reached. So this algorithm is essentially an algorithmic version of what I just said. So it has 3 steps. Until we reach mu min, we have the outer iteration, set initial point for the next outer iteration by taking the previous solution, and then update mu by reducing it by a factor of rho. So in practice, we can say that rho equal to half works pretty well. So what is going on in the outer iteration algorithm? So it is that Douglas-Redford splitting variant that I was talking about. So as you can see, it has 3 steps. The first 2 steps are computing proximal operator of the 2 split functions that I talked about. And the final step is collecting the results. So now the question is, how do we compute the proximal operator? In our Julia package, we have used for most of the functions and sets, we have used proximal operators.jl, which is a very good package. In the cases where the proximal operators were not available, we wrote the packages, we wrote the proximal operator functions ourselves. So this is our algorithm. So before I go into the Julia package, let me briefly touch upon the convergence analysis. And of course, like I am, much of our original paper actually is devoted to the convergence analysis. So as you can see, this is only one slide. So this is very brief. So this particular convergence analysis is a simplified version of what we have in the paper. So if F is alpha strongly convex and L smooth, which is a very common assumption in like convergence analysis of optimization algorithms, and a certain regularity condition hold. So this particular regularity condition intuitively means that if our data is normalized, then this regularity condition will hold. So in other words, if we have if the data is badly scaled, suppose in the data matrix we have 1 million somewhere, and then 10 to the power minus 17 somewhere. So then the data is not well scaled, and in that case, the regularity condition that we are talking about may not hold. But if the data is normalized, which is a common step for most data science type of project, so then this regularity condition can be imposed without like any problem. So if those 2 conditions hold, then for all mu in our like sequence of mu's, mu1, mu2, and so on, z mu n, which is the third iterate, it will linearly converge to the unique fixed point of the underlying fixed point operator. So that's not too important for now. More importantly, the first 2 iterates of our outer iteration algorithm will linearly converge to the unique local minima x mu of the exterior point minimization function, and this x mu will lie in that region of convexity. And as mu goes to 0, x mu will converge to x bar, where x bar is the original local minima of the original problem. So in terms of our Julia package, it's an open source implementation of our algorithm. We have extensively tested it on many problem instances, and the implementation is very fast and can be applied to large scale problems. In our paper, we have given some large scale examples too. So I will give 2 numerical examples. The first one is the sparse regression problem, where we have a given vector B, and our goal is writing it as a linear combination of at most k columns of the matrix A. So in this sparse regression problem, the cardinality constraint or the sparsity constraint is replaced with L1 norm constraint in the lasso heuristic. And I am going to compare NExOS with lasso. So this is the code that one would write. So as you can see, it's very small, 14 lines of code, and much of it is comment. So when I compare it with lasso, which is the convexification approach, on the x-axis, I am showing the size of the matrix, number of rows of the matrix, which corresponds to the number of observations. For each value of m, I have generated 50 random instances from normal distribution, and the signal to noise ratio was 20. So on y-axis, I am showing support recovery in percentage, and I am showing 1 standard error bar. So support recovery, the higher the support recovery, the better. So because it means that we are recovering more of the original signal. So as we can see, lasso is doing pretty good. It's like between 95 to 96%, but in almost all the cases, we see that NExOS is clearly doing significantly better than lasso. And this observation seems to hold for other data sets too. The other measure of quality of the solution is how small is the objective value, because we are minimizing the cost function. So for the same data set on y-axis, now I am showing the ratio of the objective value found by lasso versus the ratio of objective value found by NExOS. So we can see almost all cases not almost, like in all the cases, NExOS actually is finding a solution that has much smaller objective value, almost 6 to 14 times smaller than that of Lasso. So if we compare with Lasso, we see that in both in terms of support recovery, it's getting higher support recovery compared to Lasso and getting lower objective value. So the quality of the solution found by NExOS is better. So what in terms of speed? So one thing to note is that for Lasso, we have used GLMNet, which is a very good package for Lasso type problems. And we see that, okay, like GLMNet is somewhat faster than NExOS. So this is understandable because GLMNet is a very well-developed package tailored towards solving just sparse regression type problems, where NExOS is a general purpose package. That being said, I would say that NExOS, the speed is comparable. So how about comparison with exact method such as Gurobi? Like, for example, we know that the sparse regression problem that I talked about, one can formulate it as an integer optimization problem, and then you can solve it using Gurobi. The question is, okay, if we want to compare NExOS, which is guaranteed to provide a locally optimal solution, so how to compare? So what I have done, I have implemented a multi-threaded version of NExOS. So 4 threads, to each thread, I have input 25 random initialization. In other words, 100 random initializations in total, 25 per thread. And then I have taken the objective value solution that corresponds to the smallest objective value. So this is showing the result. On M is again the size of the matrix, number of rows. And on y-axis, I am showing the objective value of Gurobi versus the objective value of NExOS. So of course, Gurobi is solving those problems exactly. So if we have 1, so that means NExOS is finding a solution which is exactly same as Gurobi. In other words, the multi-threaded version of NExOS have found a globally optimal solution. So though it's not fully 1, in almost all cases, we see that NExOS actually is finding a solution that's quite close to the globally optimal solution. Now, what about the timing? So because Gurobi is doing a branch and bound type algorithm, so it is understandable that beyond a certain size, it will blow up, and it does. I think until size m equal to 34, Gurobi is somewhat faster, and then NExOS actually is much faster, and beyond size 50, it's not comparable, because if we go beyond that, Gurobi takes like minutes, where NExOS, the speed of NExOS is actually does not grow too much, and which makes sense because it's a first order method. So the other example that I will give is the factor analysis problem, where we are trying to decompose a positive semi-definite matrix as a sum of a positive low rank positive semi-definite matrix plus a diagonal matrix with non-negative entries. And this is the corresponding code. This problem appears a lot in statistics. So again, in this particular case, we did not have a function to evaluate the proximal operators, so we wrote the functions ourselves. So in this case, we'll compare with nuclear norm heuristic, where the low rank constraints, which is the non-convex part, is modeled as the nuclear norm of X. So when we compare NExOS with nuclear norm heuristic, we will show 2 data sets, but for other data sets too, the conclusion seems to be similar. So these are 2 real-life data sets, BFI and NEO. So we have 2 performance measures. One is objective value of the solution found, so where lower is better, and explained variance means how much of the data the algorithm is explaining. So in this case, higher is better. So in this cases, we see that for the BFI dataset, NExOS is finding a lower objective value and higher explained variance than that of the nuclear norm-based heuristic. For NEO dataset too, the conclusion, the observation seems to be similar. So though I am giving 2 examples, like in our Julia package, we have actually given many more examples and tutorials. And the final dataset, okay, so this is the Harman dataset. You can see that in this case, it's actually the gap is even higher. So in conclusion, NExOS is an algorithm tailored for non-convex learning problems, converges linearly under mild technical conditions, and computes high-quality solutions very quickly. Total iterations, number of iterations seems to be 20 to reach high accuracy, and inner iterations required by each outer iteration seems to be between 10 to 100. So with that, my presentation has come to an end. So I'd be very happy to take any question. Thank you so much.